Hey, Vlad here, devinsid.com. Welcome to another video. In the previous few videos, we started learning about implicits and type classes, and some of these videos got way too long, so I wanted to make a much shorter video, which is this one. And this one is special to me because when I was preparing the previous ones, I learned something about Haskell that surprised me. In fact, what surprised me even more was the fact that I was surprised. I'm going to explain in a second. Alright, so the first time I learned about type classes was around the year 2013, and back then I didn't really care that they actually came from Haskell. In fact, back then all I knew about Haskell was that it was a functional language, and functional language back then meant to me that they had lambdas and instead of loops they had recursion. Now, type classes are not necessarily a functional programming feature, it's just that in functional programming, as a programmer, you tend to concentrate on very small, very simple data structures and then manipulating them. And therefore, type classes are a mechanism that adds behavior to data structures. It's very natural to associate them with functional programming, and so usually they are. By the way, I have written less than 100 lines of Haskell in my entire life, so full disclosure, for the first time in my more than 100 videos, I actually have more questions than answers. So if you're a Haskell person, please consider writing a comment down below and let me know what you think. Alright, as a relatively seasoned content creator, I feel obligated to let you know that this video is not going to be some sort of rant about Haskell or Scala or any other technologies, so apologies if I upset anyone. This was absolutely not my intention. Alright, so what's this all about? My initial idea for this video was triggered by the fact that A, I was surprised by something in Haskell, and B, that pissed me off. And I will explain what it is in just a few minutes, but here's the kicker. I'm very much interested in understanding my emotions, so I went on my usual thought path, and by the end, it dawned on me. It wasn't the fact that I was surprised by something in Haskell. As I just mentioned, I've written less than 100 lines of code in Haskell. It was the fact that since 2013, I've read a dozen of blogs about type classes, both in Haskell and in Scala. I've seen plenty of videos about type classes, both in Haskell and in Scala, and none of them even mention that. Now, why am I making such a big deal out of this? I'm making such a big deal out of this because plenty of people in the Scala community actually love Haskell. So when I read those articles, I assumed that those people knew Haskell, and then I was disappointed that they didn't mention this very, very subtle detail. You have to understand that in the Scala community, Haskell has this impeccable status. It's like it's on the pedestal. It's like it can walk on water. It's like one day you will ascend to it and will never look back. All right. I talk too much. The subtle detail is about how type class instances are being created for simple data types versus for algebraic data types. Let me show you how it's done in Haskell. What we have here is my Chrome fully maximized, and we're on a website called REPL.it or REPL.it, and we're running a Haskell interpreter. So there's some Haskell code over here, and this is the output. So I'm just going to walk you through this code because I know that most of my videos are about Scala. So this is an algebraic data type. So we're defining a data type called traffic light, and we're saying traffic light can either be red or yellow or green. And this little thing is not super important right now, but there are type classes behind it. So there's a type class called EQ, which stands for equality. And with this thing, you're allowing Haskell to automatically generate an instance of the equality type class. But again, we're not talking about this today. So over here, we're creating our own type class. And as I mentioned in my previous video about type classes, in Scala, you actually have a language level keyword called class to generate a type class. And what you have over here is generics, right? So this is just a parametric type. So you have a type class of some type T, where you have a method called asString or a function called asString, and this just delimits the signature of that method, right? So this method has a signature that a T comes in and a string comes out, right? So this is a typical type class, and in just a second I'm going to show you exactly the same thing in Scala, so no worries, okay? Haskell obviously also has a language level support for creating instances of the type classes. So you're creating an instance of this type class for the type of traffic light. So T becomes traffic light, where the method asString, and this looks like overloading, but this is how you do pattern matching in Haskell. So you say if asString receives red as a parameter, then the result going to be the string red, right? So T comes in, string comes out. green is green, yellow is yellow. Okay, and now we have an algorithm over here which has a dependency on an instance of this type class. It says, okay, give me an instance of this type class for some type t, and then I will allow you to give me a t and I will produce a string. So we have a method called algorithm, and t comes in and string of t comes out. So in Haskell, you don't need to somehow magically retrieve the instance from the implicit scope. It's just there, so you can just call string because this type class is there, right? So you can just call string with a t, string comes out. Now this is a main method. Again, the first line is the signature. It returns, in Scala it would return a unit, in Haskell it returns an IO of void. I believe it's called void in Haskell, something like unit. And so we have this thing which is basically a full comprehension in Scala. I think it's called a do comprehension in Haskell, but I'm not sure. And we're just printing out, we're calling algorithm and we're passing red. What comes out is a string called red. We're calling algorithm with green, green comes back. Calling algorithm was yellow, the string of yellow comes back. Now we'll get back to this code in just a second, but let me convert it into Scala because let's face it, most of you guys are better at reading Scala than Haskell. As always, we're in the Ubuntu virtual machine and we're running Sublime Text, the editor of my choosing, which is fully maximized, and we're using a wonderful plugin called Terminus, which emulates the entire terminal for us, which runs SBT, which we're using to rerun the main every time we save the file. So what we have here is a simple Hello World project. I'm just going to run you through all of the files real quick. So we're using SBT version 0.13.6. In our build, we don't have anything special except for implicits, the compiler flags for implicits. We're using Scala 2.12.4, and we have single main file with a Hello World application, which you see running at the bottom. I'm going to minimize the sidebar like this. All right, so let me remove the Hello World and let's implement this type class example. So if I type in ADT and I press tab, my Sublime will generate the typical encoding of ADTs in Scala. Now I'm going to call it traffic light, and if I press tab, my code will be over here. And in fact, let's use an abstract class over here, abstract class like this. Now you don't need the extends product with serializable, but if you do, it will actually be better. And in fact, I'm going to show you an example by the end of the video, so I'm going to comment it out like this. All right, so in this object traffic light, we're going to have a case object red extends traffic light, and I'm going to duplicate the line a few times, so I'm going to have red, green, and yellow like this. Okay, so now we're going to go down a little bit like this, and we're going to have a trait, which is a type class. It's not a language level feature in Scala, so we're using traits. This is a type class for t, has a function called string. T comes in, string comes out, the same as in Haskell. Now we're going to have an algorithm that wants an instance of this t, right? So it wants an instance of this type class like this. This is the notation. This is called a context bound. Rewatch my video about type classes if you don't know what I'm talking about. T comes in, string comes out, and all it's doing, it has to implicitly retrieve the instance of this type class by using the implicitly function, which is in predef. So we're asking it to give us the instance of the type class for t, and then on that instance we're calling as string and we're passing in the t. All right, let's save the file. Let's see if it's working. All right, it's working. Okay, so let's continue. So now we need an instance for this type class, and we're gonna define it over here, val instance, and it's a type class of traffic light, same as in Haskell. If you haven't watched my video about type classes, it is always preferred to use vals instead of objects. Okay, now what I have forgotten to mention in the video about type classes is that instead of creating an anonymous type class, an anonymous class over here, right? So instead of saying it's a new type class for traffic light and going over here and saying override def as string, what we can do instead is we can go and straight pattern match on the instances of traffic light, and then because type class is a single abstract method type, also known as a sem type, Scala will automatically convert this lambda, this partial function lambda, into an anonymous class of type class. So all we need to do over here is we need to say case traffic light dot red. And then we're going to use some fancy ANSI codes over here. I'm going to say red, always reset them and duplicate that, okay, a few times. So over here we're going to have red, green, yellow, over here, red, green, yellow, and over here, red, green, and yellow. like this. Now we're going to create a few traffic lights. What's happening? Traffic light dot, oh, sorry, this one should be red like this. All right. So what we're going to do now is we're going to create a few instances, right? So we're going to say, okay, the traffic light is traffic light dot red. We're going to have green like this, and we have yellow like that. Now these are already objects, but I want to show you is subtype polymorphism here, right? It's going to be important in just a few seconds. So it is important here that we're using rad as a traffic light and not as a rad.type. Okay, you'll see it in just a few seconds. Okay, and now same as in Haskell, we're just going to print them out, right? So we're going to print out the algorithm applied to rad. We're going to do the same thing with green, and we're going to do the same thing with yellow. Let's see if I made a typo anywhere. No, I didn't. There we go. Red, green, yellow. Same example as in Haskell. All right, as I said, the topic that we have today is the difference between creating type class instances for simple types and creating type class instances for algebraic data types, which is what we have over here, right? So the problem is that what you see over here is something that I have never seen in a Scala blog about type classes. And the problem is that in Scala, there is a sort of a better way to do this, and therefore nobody even talks about this one. And the problem with this one is that if you forget, for example, green, then everything still works fine. Now you get a warning, right? You get a warning because we have a sealed abstract class, which means that the compiler knows about all the instances, right? It knows that there is red and green and yellow, and therefore it says, hey, by the way, you forgot to match on green, right? So the match may not be exhaustive. It will fail on the following input. Now in Scala, you can also have a special compiler flag that will convert all the warnings into errors, and this is what we're going to do now. We're going to go to our build file, and we'll enable the warning over here. Now it's called like this, X fatal warnings. Now the problem with this flag is that the console, right? So if we were to jump into the REPL from the SBT, it doesn't really know how to work with the X fatal warnings. So what you usually do is you make sure that the Scala options during compilations have this flag, but the REPL doesn't. So I'm going to show you how to do that real quick. There are multiple ways. The one that I prefer is to say, okay, so these are going to be the console options. And it's going to be this sequence, but without the fatal warnings flag, right? So it's going to be just over here, but without this warnings flag, okay? And then we're going to say, okay, so the Scala C options only in the compile and console, right? They're going to be console options. However, all the other Scala C options, right, like this, we're just going to add to them the console options plus the sequence of this new flag -x fatal warnings, right? So basically the console, the Scala C options in the console are not going to have this fatal warnings flag, okay? So this is what it's doing. We're changing the build file, therefore we need to reload the entire project like this. All right, and if we try to run, in fact, even if we just try to compile, it says the same thing, but now it's actually a compilation error. Now, what's interesting is that in Haskell, the same thing will happen, right? So if I comment this out, all of a sudden, there will be an exception. Now, I'm sure that Haskell also has some magical compiler flag that will convert this into an error, but first of all, I was surprised that this is how the instances are encoded in Haskell, and also I was surprised that Haskell even had exceptions. I thought only in pure languages like Java or C# or Scala had exceptions, but everything in Haskell was type safe. I thought it was a freaking heaven. Also, I mentioned in the beginning of the video that I was surprised by the fact that I was surprised, and I'm going to explain this in just a few minutes, because it's actually not surprising at all that the instances of the type classes are encoded exactly like this, because I believe that there is no other way. Now, let's enable this one real quick. Okay, so let me show you how this is usually shown in the Scala world, so to say. In the Scala world, if you have rad and you just say traffic light dot rad, then the Scala compiler will infer the most specific type because Scala has subtype polymorphism. So this is not going to be traffic light; it's going to be traffic light dot rad dot type, and the same thing is going to happen for green and yellow. Green, yellow. This one is green, and this one is yellow. Okay? All right? Obviously, I can't give them the same names. I'm going to call this one more specific red, and this one is going to be come on, more specific green, and this one is going to be more specific yellow, like this. So now the compiler is happy. The thing is that now if we're trying to print it out, let's try to print out the algorithm of more specific red. I wanted red. There we go. Okay. Now the compiler will say, hey, I couldn't find an implicit value for evidence parameter of type class red. So basically, even though there is a type class for, even though there is a type class instance for traffic light, there is no type class instance for specifically red. So what we're going to do is we're going to comment out these print lines, and we're going to comment out this entire instance. And instead, and this is what you usually have in Scala, is that you have instances for every individual type. For example, you have an implicit val instance for red, which is a type class not for traffic light, but it's a type class instance for traffic light.red.type. Okay, and it is the same thing. It's an add expansion. Something comes in, and the only thing that can come in is red, and console.red plus red plus console.reset comes out, and now it's going to work for red. Now obviously it's not going to work for green or yellow because we just don't have instances for them. In fact, maybe we should have them real quick, like this. This is an instance for green. Yeah, hold up, let me enable case sensitive search. Okay, so now I can mark, come on, I can mark red over here and do this, and I can say that this is a green, and this one is caps. The last one is this implicit val instance for actually let's copy this whole thing like that, and whoops, like that, and we're gonna have a yellow over here, and we're gonna have yellow over here, and now we can do this one with more specific green, and this one with yellow like that. Man, that was hard to type. I don't know why. Now, what's interesting is that even though it works for all the instances now, if we take, for example, this code and bring it down, under the instances, okay, and we try to use it, and it's going to say that it doesn't work, right? Because it says, okay, this is a traffic light. Even though we have an instance for every possible instance of the traffic light, this still doesn't work. Now let's comment this out again. I'm going to show you how to fix this in just a few seconds, but think about it. This is like what all of these blogs showed me, and this is better, right? This is more type safe. You have an instance for red, you have an instance for green, you have an instance for yellow. There are no warnings, there are no magical compiler flags. Now there's an issue with subtyping, but as I said, I'm going to show you in just a few seconds how to solve this. But in general, it seems better, right? It seems better than Haskell. All right, this is the important part. I always thought, because all of these blogs showed me only this version, I always thought that this is exactly how it is implemented in Haskell. And this is the part where I was surprised that I was surprised. I was surprised that the way it's done in Haskell is like this, right? By pattern matching on the supertype. And then I was like, hold up. What's supertype? Haskell doesn't have subtype polymorphism. So if traffic light is not a supertype of red, then what is the relationship between those types? And the answer is there is not. And you know why? Because red in Haskell is not even a type. So if we were to encode type classes in Scala more closely to Haskell, then it would actually look like this. We would still have a sealed abstract class. I'm going to call it traffic light 2, right? Just traffic light 2. And then we would have an object traffic light 2 like this, okay? And now this is important. What we're going to have here is just vals. We're going to have a red, and the type of red is going to be traffic light 2, right? There is no type red, and this is just going to be an anonymous class, right? Like this. And the same thing for green and yellow, like this, right? And the instance, I'm going to copy that one like this, okay? And I'm going to paste it over here, right? And I'm going to say that this is an instance 2 of traffic light 2, and the rest pretty much stays the same. I'm just going to put a 2 over here. Now Scala doesn't really understand that, and it says that, no, I'm sorry, that's not what I wanted to show you. This has to be traffic light 2, 2, and 2. The compiler thing, the pattern matching thing doesn't really understand that we actually matched on all the possible instances, right? Because this is a sealed abstract class. So anyway, so what we need to do is we need to add another one, even though it's never going to happen. So we're just going to say over here, sorry. Right, so now the compiler is happy. Okay, so what we can do now is we can go down and take this code, for example, the original one, right? And we can call it over here, but we're gonna call it on. Okay, we can go straight to traffic light dot red, traffic light dot green. Red should be like this, red, green, and yellow. Now let's not forget the 2 over here, like this. Okay, so as you can see, it works now, and this exactly the same thing did not work before, because before we only had an instance for traffic lights, but not for red and green and yellow. And now we don't even have the situation because red is not even a type. So the only thing that you can define an instance for is the traffic lights, and this is exactly why it's done in Haskell, because you can only define a type class for some type, and if red is not a type, then you cannot define an instance for it. And this is an open question that I have. Isn't this encoding, this new one that I showed you, somehow better? I mean, the original encoding had more types, so having more types seems, more type safe. It seems kind of better. But if you've been around the block for quite a few times, the less you encode, in the end, seems to be somehow better, because you just don't have to worry about all of these possibilities, all of these, all of these. I don't know, for some reason I want to say the word mechanics, right? So sometimes like having less is actually better. Encoding less is better. The sort of the simpler your code is, the better. So if you don't need those extra types, then why have them? But seriously, this is an open question. I really don't know which one is better. Now, obviously, this one does not have syntactical support as the other one has, but I believe these days it could be helped with some fancy macros compiler plugin or something. So for now, enough conspiracy theories. Let me show you how to deal with subtype polymorphism versus type classes, the issue that we had just a few minutes ago. So let me just remove this second encoding. We don't really need it. Also remove the instance. And let me go down and remove this one as well over here. All right, so this is what we had. I'm gonna remove I'm gonna comment them out. I'm gonna comment out the instances, like the individual instances. I'm gonna comment in the instance that is for the entire traffic light. And the issue that we had was that we couldn't, which way was it? This one didn't work, I think. Yeah, this one didn't work. So we couldn't use the specific instances, because the only instance that we had was the big one, right? The one for the traffic light. Where is it? This one. Okay. So the way you deal with is there are actually 3 different ways. The first one is that if you have access to your type class, so if the type class is yours, then you can make the decision to make the T contravariant over here, like this. This should solve all the issues, right? So this solves the issue, and now it works for this, and I believe it should also work for that. Right, so it works for both of them. But if you don't have access to the type class, so if the type class is not yours, and in fact, most of the times, these type classes are defined with an invariant position, then what you can do is you can go to the algorithm and tweak the algorithm a little bit. So first of all, let me convert the algorithm into the Shugart syntax, right? So we're just going to say that a T comes in, right? And then the second parameter is going to be an implicit. We usually call it instance, but I'm going to call it evidence, or EV. Sometimes it's called evidence, right? That the T is a type class of T. Okay, so this is exactly the same code, and now we don't need this fancy thing because we have access to the evidence, right? So we can say evidence dot a string. Okay, so this is exactly the same code. It works exactly the same way. I'm going to comment. I'm going to remove the commented outline. Okay, so the other thing that you can do is, if I remove the contravariance, it's not going to compile again. But what you can do is you can go over here and you can say that you don't need a type class for T. You want a type class for some super type of T, and you don't even have to name it, right? So if you do it like that, the code is also going to work, right? So if you have access to your type class, you can fix it there. If you don't, but the algorithm at least is yours, then you can fix the algorithm. And if you don't have access to either of them, then this is what you should do. Let me remove that again so that it doesn't compile. Okay, like this. And basically what you do is you have the instance both for the traffic light and both for the specific ones. In fact, I'm going to move them up a little bit like that, so we have them under each other, like this. Okay, so we have the instance, and let me go down over here a little bit. Okay, so we have the instance for the traffic light, and now if we also have the instance for each individual type, then the compiler should be happy. The compiler is happy, and now we can also reuse a little bit of code over here. Instead of doing all of that, we can just say instance dot as string, right? So we can basically just call this code, and it will be the same thing, right? Instance dot as string, the same thing over here, right? I'm gonna say instance dot as string, exactly the same thing. And in fact, in Scala, you can actually have this even more minimized. Instead of having a val over here, we're gonna have a def. We're gonna call it multiple instances now, because technically it is multiple instances. And you say, okay, so we're gonna be parameterized, and we're gonna be parameterized with traffic light. And the same as we did with the algorithm, right? We said, okay, give me the super type. This is sort of the other way around. We say, okay, this is not an instance for the traffic light. This is gonna be multiple instances for any subtype of traffic light. Okay, so this is going to be a type class, not for traffic light, but it's going to be a type class for the subtype. And traffic light itself is a subtype of itself. Okay, so this is all we need to do. Now we can comment out those instances, right? And it's exactly the same code, and it's shorter. And I told you that I will show you a better way how it's done in Scala. Now, all of these solutions actually solve this problem, but sometimes this is actually not the problem that you want to solve. Sometimes it's not a problem. Sometimes you want your code not to compile if an instance for some specific type is missing, or in other ways to express this, you want your code to work with some instances and I'm sorry, with some types, but not with the others. And I'm going to show you this example. And this is the one that I mentioned before, that I said by the end of the video, I'm going to show you one of the benefits of this encoding. So what we're going to have is we're going to have a completely different type class. We're going to have a type class called blinking type class. It's parameterized for t, right? And instead of s string, it's going to have a function called blink. Let's get some t, and string comes out. So now instead of algorithm, we're going to have blink. And blink is going to need the instances not only of the type class, but also of the blinking type class, right? So both of them. So if you're not used to this, first of all, get used to this. But basically, this is an implicit parameter list with two parameters, okay? So now it's going to get the t, okay, of string. And now we're going to construct an s by implicitly resolving the instance, resolving the instance for the type class of t, and this one has a method called sString. I'm going to pass it the t. Then we're going to construct a b, which is implicitly the other type class, right? So it's the blinking type class for t, and it has the method called blink. I'm going to pass it the t, and we need to produce a string, so we're going to use string interpolation. We're going to say $b space $s. Okay, so now what we're going to do is we're going to create an instance for only the yellow case, for example, right? We're going to call it yellow blink instance, right? So we're not defining it for the entire traffic light. We're only defining it for the yellow. So we're going to say it's a blinking type class for traffic light of yellow dot type, specifically this one, okay? And we're going to use the sem types over here, right? Just a lambda. And we're going to say console dot yellow plus blinking plus console dot reset. I'm going to do the same thing for green, right? So I'm going to go over here. I'm going to say, okay, like that. This is going to be green. This is going to be green. Let me duplicate that line. Go over here and say that this one is also green. Let's see if that compiles, or if I did some typo somewhere. No, I didn't. Okay, so let's try and use that now. So we're going to print out, and instead of algorithm, we're going to print out blink of more specific yellow and more specific green. Also doing red, always doing red, green, yellow. Let me put green above yellow. Okay, like that, like that. Okay, so now that should work. Okay, so we should see blinking green, blinking yellow. If you obviously try this for red, then it doesn't work. In some countries, if you have, the traffic light, then only the yellow blinks and only the green one blinks, but not the red ones, right? So this is the way to encode that. I don't think that this is even possible in Haskell because, as I said, red and green and yellow, they're not even types on their own. So I'm not really sure how it is useful in Scala. This is an honest question. I'm really not sure how useful that is, because let me show you this. So if you use instead of more specific green, if you just go and use green, right, it's not going to work. And this means that if you have, let me comment this out. if you have, for example, a list, right, of even though you're using more specific green, right, and even though you're using more specific yellow, right, and you have instances for both of them, okay, and then if you go and do for each, you have the light, right, and you try to do the same thing, you say print out blink light. So you have the instances for both of these types, but the problem is that the type inferred over here is not a green or yellow or something. In fact, maybe this will become possible in Scala 3 because Scala 3 has, I believe they're called union types, but at least right now in Scala 2 this is not possible. So the type that the compiler infers is traffic light, right? So because this is a traffic light, in the end you're forced to pattern match on that light again, right? So what you need to do is you need to say, okay, so if this is a traffic light dot red, then I'm just not going to do anything. And if it's the other ones, right? So if it's a traffic light dot green, right? And I believe you can actually do an or here, right? So this is sort of like a union type over here. I believe you can do that. So if it's a traffic light green or traffic light dot yellow, and this green should be small green. Okay, then you just print out blink of light. Let's see if this works. I'm not really sure if this is going to work. What does it say? I couldn't find implicit value evidence parameter of type blinking type class traffic light. Okay, it doesn't understand this, I believe. Let me try that. I'm not sure if it's going to work like this. I'm just playing around here. Hold up, like that. No, it doesn't work like that. I believe we could do something like this. Type yellow dot type. No, still doesn't work. All right, so we have to basically do it manually. So we have to say if light is a green one, like that, then do this, and otherwise if it's a yellow one, then do this one, and I believe this one should work. Yeah, so this one actually works. So yeah, because you have to pattern match on it, I'm wondering if this encoding is actually, somehow useful or not, right? Because you can solve this with overloading or some other ways. All right, that's all I got for you today. As I mentioned in the beginning of the video, I actually have more questions than answers. So if you're a Haskell person, please let me know. Maybe there's a way to encode something like this in Haskell with some extensions or something else. If you're a Scala expert, what do you think? Maybe the community should invest into some macro to also allow the other encoding, or maybe this should be something for Scala 3. I really don't know. As a reminder, I did not want to upset anyone. I did not want to bash on any technologies, Haskell, Scala, or anything else. Really, I'm sorry if I did upset you. All right, that's all I got for you today. It's been Vlad, devinsideryou.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.